Hi guys, welcome back to the channel. In this lecture, we are going to discuss one problem on 3-span continuous beam in which we need to find the plastic moment capacity for this beam, right? And we are considering this beam as prismatic. Okay, if you are considering that this beam is prismatic, so this MP moment will be constant. This plastic moment capacity will be constant for this whole beam. Okay, so this is a 3-span continuous beam. Okay, and this support is A, this is B, this is C, and this is D. Okay, so as you can see that we need to calculate the plastic moment capacity for this beam. First, we need to identify whether this structure is static, indeterminate, or determinate. Okay, so as you can see that this continuous beam is statically indeterminate, and this static indeterminacy will be one reaction is acting at this point, one moment will be there. Here one vertical reaction, one vertical reaction, one vertical reaction. Okay, so total number of reactions are 5, and I'm not considering any horizontal reaction. Okay, so 5 minus of equilibrium equation will be 2, that is summation fx, summation fy 0, and summation fz 0, summation mz 0. Okay, so this equals to 3. So static indeterminacy of this beam is basically 3, right? So number of plastic hinges required for the collapse, for complete collapse of this structure, number of plastic hinge required will be 3 plus 1, that is equals to 4. And this 4 plastic hinges, if the 4 plastic hinges will form in this structure, whole structure will collapse. Okay, so corresponding to 4 plastic hinges, whole structure will collapse. Okay, so in the last lecture also we have seen that in the continuous beam, critical cases will be our individual spans. Okay, we need to check the cases for individual spans, right? So let us discuss this thing in detail. So if you are saying that there is complete, the 4 plastic hinges are forming on this beam. Okay, so this is our structure. This is our continuous beam. Okay, and we are saying that the four plastic hinges are formed for the whole structure, for the structures to be, if the 4 plastic hinges are formed on this structure, the structure will collapse. Okay, there is the whole structure will collapse. What is the meaning of this thing is that, let us suppose the first plastic hinge is forming at this support A. Okay, second plastic hinge will form under this point load, right? Third plastic hinge will form at this point, let us suppose, and fourth plastic hinge will form either at this load or at this load, whichever is critical. So I'm assuming that it is forming under this load. Okay, so here you can see that the 4 plastic hinges are formed, and during the collapse this beam will deflect like this. Okay, so this is the you can say that this is the collapse deflection at the deflection during the collapse, right? So you can see that the whole structure is collapsing. So 4 plastic hinges are required for complete collapse of the structure. Okay, but if you check the individual span, for the individual span, let us suppose the first plastic hinge is formed at this point. Okay, and if you are checking the individual span, collapse of the individual span, the second plastic hinge will form under this point load. Okay, moment will be maximum over there, and third plastic hinge will form at this point, right? So you are getting one deflection, one plastic collapse like this. Okay, similarly, if BC portion is getting collapsed, okay, if BC portion is getting collapsed, the deflection diagram will look like this. Okay, one plastic hinge will form at the center of this BC portion. Okay, similarly for this CD portion, the deflection during the collapse will look like this. Okay, so you can see that for this portion, 2 plastic hinges are required. Okay, for this portion to fail, 3 plastic hinges are required. Okay, again for this portion, 2 plastic hinges are required, right? Okay. So critical case will be from this one, from here only. Okay. So if you calculate the moment capacity from this point, let us suppose if you are calculating the moment capacity by considering the whole collapse of the structure, let us suppose this value comes out to be MP1. Okay. And if you are calculating this, considering the collapse for this span, if you are considering the partial collapse for this AB portion, and let us suppose its moment capacity is MP2. Okay. And it's for the BC span, the moment capacity comes out to be MP3, and for CD span, the moment capacity comes out to be MP4. Okay. And I'm assuming that MP is greatest, MP2 is greatest amongst MP2, MP3 and MP4. Okay. But remember that MP1 will always be less than of MP2, MP3 and MP4. Okay. So this can't be our collapse. This MP1 will be less than equals to MP2, MP3 and MP4. Okay. This cannot be our collapse. Okay. This is not a critical value. Critical value will be always be one which will give the greatest moment capacity. Okay. Because we need to design our structure for the maximum so that the structure won't fail. Okay. And you are considering that if the whole structure is getting collapsed, if you are distributing the loads along the whole structure, if the whole structure is getting collapsed, the value of MP comes out to be very less. Okay. Right. In the previous problem, we have discussed that when you are considering the whole structure is collapsing, the load factor comes out to be maximum. Okay. But here you are fixing the load. So moment should be minimum if you are considering the whole collapse of the structure. Okay. So in case of the continuous beam, you need not to discuss, you need not to calculate this MP1. Okay. You will be always checking individual spans only. Right. So now we will be calculating we will be checking the moment capacity for this individual span and calculate which moment, and we'll see which moment will come maximum. Okay. And in this problem, we will be solving this problem using static equilibrium method. So now you can see that the static indeterminacy of this beam is 3. Okay. So 3 redundants will be there. 3 redundant reactions will be there. Right. So I am taking MA as one redundant, MB and MC. Okay. So I need to divide this beam into 4 parts. First part, where we have released the redundant reactions. There will be one internal hinge because we are considering MB as redundant, and initially we are removing that redundant force. Okay. At C also there will be one internal hinge. This is D support. Sorry. This will be okay. There will be one horizontal reaction. Okay. So now you will see, now we will be applying the loading. This 45 kilonewton load. Similarly, for this BC portion, there will be 30 kilonewton meter. This distance is 4, this is 4, this is 6, right? And here this load is 60 kilonewton, this point load is 60 kilonewton, and again this load is 60 kilonewton, right? So this distance is 2, 2, 2. Okay, so this is the first case. Now we'll be applying the redundant forces. Okay, so this will be our case 2. there will be internal hinge because we have released the redundant force, and we will be applying the moment in this direction, this MA. Okay. Similarly, will be for the B part, for this MB, we will be applying the redundant force like this. Okay, this is A, this is B, there is internal hinge over at this point C, and this is D. Okay, now for this this CD part, for this MC redundant, it will look like this. There is internal hinge, see that C. So again, okay, so the effect of these four structures will give the effect which will be given by this structure. Okay, this statically indeterminate structure, right? So now we will be forming the equilibrium equation in terms of moment. Okay, so what to do next? Next step is to draw the bending moment diagram for this loading case. Okay, for this loading case, we need to draw the bending moment diagram. Right? So at this point, the moment will be 0. These 2 points, at this point also the moment will be 0 because it is simply support, this is internal hinge, and at this point the moment will be 0. So if you calculate the moment, the maximum moment at this center will be, it will be 45 into PL 4, 90 plus W is 10 L square, 8 square divided by 8. So this value comes out to be 170 at this center. Okay. And we are considering the sagging as positive, sagging moment positive. Okay, so this loading is inducing sagging moment on this AB portion. Okay, next let us come to point this portion span BC. For the BC portion, the diagram will look like this. Okay, and the maximum value of this load will come at the center. Maximum value of the bending moment will be at center, so it will be 30 into 6 square divided by 8. So this value is 135 kilonewton meter. Okay, and this will also be sagging. Right, now again let us come to this point. Its bending moment diagram will look like this. Okay, so bending moment will be, this reaction at 60 into this will be 120. 120 here, 120 here. Okay, so the maximum value of the moment for this portion is, for this section is 120, for this section is 135, and for this section is 170, right? So, and all these moments are sagging moments. Sagging here is considered positive, right? Now let us come to this part, this beam, this second part, this beam. Okay, in this portion we are applying the moment MA. Okay, why we have chosen this direction? Because I am assuming that, again I am drawing this. Okay, so when the plastic hinge is formed at A, it will deflect like this, right? So to against this rotation, there will be moment induced, which will be MP. Okay, so that's why I have taken this direction is anti-clockwise over here. Okay, so if you draw the bending moment diagram for this case, let us draw this figure again. and you are applying the MA moment over here. Okay, so this is here, there is internal hinge. Okay, so the bending moment diagram will look like this. This is negative. Okay, this value is negative because this is inducing hugging moment. Okay, similarly, if you consider this thing, okay, you can calculate the moment. Okay, it is not difficult. You can get this moment diagram if you solve the equilibrium equation in terms of moment. Now let us come to this thing. Again, this figure, let us draw the bending moment diagram directly. So it's bending when you are applying the MB moment at this point. So its bending moment diagram will look like this. Okay, in this portion there will be no bending, right? So this is MB. Okay, similarly for this portion, the bending moment for this thing, for this beam, the bending moment diagram will look like this. This will be MC, and you can see that all these bending moments are negative. Why negative? Because these are sagging moments. Okay, so this thing is done. Now we will be writing the equilibrium equations. So now let us first consider this portion, this AB portion. Okay, for the AB portion, the plastic hinge will form if you want to collapse the AB structure. Okay, this AB portion, the plastic hinge will form at A under this point load and at B, because the moment will be maximum at this under this point load only. Okay, so if you think that if the plastic hinge is forming under this load, okay, we will be writing the equilibrium equation. Let us suppose this is E. Here the plastic hinge point is F, and here it is, let us suppose, G, or this is H. Okay, so equilibrium equation for ME, if you write, if you want to calculate the moment at this E point, okay, when the plastic hinge is forming at this E point, it will deflect like this. The moment here is sagging moment, so this MP will be positive, right? So if you write the equilibrium equation at this point E, okay, so what will be our equation? ME equals to 170 minus of MA at this D point, E point, this value will be MA by 2 through linear interpolation. Similarly, at this point, the value will be minus of MB by 2, right? And at C, this portion is 0, so the effect of this M is not coming on this AB portion. That we can see through this bending moment diagram. So this will be equals to ME. Okay, so for the plastic collapse, MA will be equals to MP, and again MB is equals to MP. We are not taking MA equal to minus MP because we have already considered the direction over here. Okay, we are taking this MA as negative side, right? So no need to consider MA equals to minus of MP. So if you solve this thing, and ME will be equals to MP. So this will be 170 minus of MP by 2 minus of MP by 2, right? So this will be 2 MP equals to 170. So MP comes out to be 85 kilonewton meter. Okay, so MP1 comes out to be 85 kilonewton meter, right? No doubt should be in this. There should be no doubt, okay, in this, how we get this MP value 85 kilonewton meter, right? Now let us consider the plastic collapse for this BC portion. Okay, remember that we are checking the individual spans over here. Okay, so if you consider the plastic collapse of this BC portion, again we will be writing the equilibrium equation. For the plastic collapse of BC portion, the plastic hinge will form at B and at the C, and that's at the midpoint. So during the deflection, it will during the collapse, it will deflect like this. This is the direction of the rotation. Here the direction of rotation is like this. So to oppose the direction of rotation, there will be moment mp, and here again the moment will be mp. So moment mp is sagging over here, so it will be positive. So if you write the equilibrium equation at point F, so it will be mf equals to, this is 135 minus of 135, again at this the effect of MB will not be there in MB in this BC portion. So due to MB, this force will be, this moment at this F will be minus MB by 2. Okay, and again due to MC, the moment at F will be minus MC by 2, right? For the collapse, MB equals to MP and MC equals to MP. Again, I am not taking the minus MP because we have already taken this MB MC as negative. Okay, so MF will be MP, sagging moment, and this is 135 minus of MP, right? So again, this will be 135 equals to 2 MP. So MP comes out to be 67.5 kilonewton from here, right? So MP2 comes out to be 67.5 kilonewton meter. Okay, so this is the thing. Now let us calculate the equilibrium equation for this CD span, moment in CD span. Okay, so as you can see that there are two critical points. One is this under this load, or one is under this load. Okay, we will check individually for which the moment value will come out to be maximum. That will be our critical case. Okay, so now I'm assuming that for CD span, I'm assuming that the plastic hinges are forming at C, H and D, not D because D is already a hinge support, at C and H, right? So if you write the moment equilibrium for MH, it will be again equals to, if the plastic hinge is forming at C and H, it will deflect like this. This is H point. The moment induced MP will look like this. Here also MP will be there. Okay, so MH I can write 120 minus 120 is this moment, minus due to B load, due to this MA, there is the MA load, MA moment is not affecting this span. Okay, so there won't be any moment over here due to this MA load, and again due to MB there is no bending moment at this CD portion. Okay, and due to MC by linear interpolation, so this is 2, this is 2, this is 2, so this will be MC by 6 equals to X by 4. So this will be 2 by 3 of MC. So this will be 2 by 3 of MC. So moment at this point, this H point is 2 by 3 MC, and that we have calculated using linear interpolation, right? So for the plastic collapse, MH equals to MP. This is equals to 120 minus 2 by 3 into MP, right? So this value will be 5 MP by 3 equals to 120. So this will be 120 into 3 divided by 5. So this will be this is 2 by 3. Okay, this is 2 by 3. This is 120 minus of 2 by 3, 60. Okay, so this value comes out to be 5. 2, 4. So this value is coming out to be 72 kilonewton meter. Okay, so this value comes out to be 72 kilonewton meter, right? So MP3 is 72 kilonewton meter, right? Now I am saying that the plastic hinge is forming at this D point. Okay, we need to check, sorry, not D point, this G, under this G point. Okay, either plastic hinge can form under this point load or this point load, because moment is maximum at 2 points, and we will check which will be our critical case. Okay, Now, again for CD span, I'm assuming that the plastic hinge is forming at C and G. Okay, so I need to write equilibrium equation for the moment at mg. Mg equals to 120 minus of moment at this will be again mc by, if you use the linear interpolation here, mc over my 6 equals to x over my 2. So mc will be mc over mc. So at moment at this point will be mc by 3, right? So this will be for the plastic collapse, mc equals to mp and mg equals to mp. I'm not writing again mc equal to minus mp because I have already taken mc as negative, right? So this will be mp equals to 120 minus of mp by 3, right? So this will be 4 mp by 3 equals to 120. So mp comes out to be 90 kilonewton meter. Okay, so you can see that mp value comes out to be 90 kilonewton meter. Okay, mp4. So the critical bending moment, design moment will be 90 kilonewton meter. And if you consider these cases are when we are considering partial collapse. What is meant by partial collapse? Means individual spans are failing. Okay, I'm not saying that here there is complete collapse of the structure. And if you calculate the plastic moment capacity using complete collapse, so this value will be minimum. So this value will be less than, let us suppose that value is mp5 will be less than from all these value. Okay, mp1, mp2 for complete collapse, right? Then this thing we have already discussed in the starting of the lecture. So our design moment will be 90 kilonewton meter. Okay, so now let us draw the plastic bending collapse diagram. Okay, plastic bending moment diagram at the plastic collapse. So the critical case is the one in which the plastic moment capacity is maximum. Okay, so the plastic hinges are formed at this C point, at this D point, right? Okay, so at this point the bending moment is, this point the bending moment is 0, and this point the bending moment is mp. Okay, and again at this B point the bending moment again will be mp. And again at this A point the bending moment will be again mp, right? So what we will do, we will join these moments. Okay, and if you see now, if you draw the individual bending moment diagram of the collapse, what we are doing, that we are just adding these two bending moment diagrams. Okay, this is due to load and this is due to the reactants basically, right? So if you draw okay, so as you can see that if you analyze this structure, okay, the moment will be maximum. These are the critical moments point. Okay, this A, this B and this C. Okay, at these point the plastic hinge will form, definitely form, or the moment will be or the plastic hinge will form at this A, this B and this C point. Okay, these are critical moments, right? The critical points. Okay, if you see the elastic analysis, if you solve this beam using elastic analysis and draw the bending moment diagram, you will find that the moment will be maximum coming at these 3 points. Okay, so chances are there, very 99% chances are there the plastic moment will be there, okay, at these points. And if you calculate the value of this thing, this is positive, here this is negative, this is negative, okay, this is negative, this is negative, right? So we just overlap the bending moment diagram. Okay, this is due to the reactant force where the plastic hinges are forming, and this is due to what you can say that this is due to the individual load. Okay, so if you overlap, how do you get this straight line? If let us suppose this becomes MP over here, and if this is MP, this MP becomes MP. So if you add these two things, it will give you this straight line. Okay. Similarly, here also, this is MP. If this MB value becomes MP, this MC become MP. If you add these two things, this will become this straight line, right? So this bending moment diagram, this red bending moment diagram, if you add all those things, I'm assuming that this MA will be equals to MP, this MC equals to MP, and this MB is equals to MP. So if you consider this thing, you will get this red line. Okay, and after that you overlap due to loading. The bending of you overlap due to loading. Okay. So here you can see that the MP value is negative. So this value will be, this is what, 90 into 2 by 3. So this is 60. So this is 60. No, this is not 60. This is, if you calculate 90 by 6 equals to x divided by 2. Okay. So this will be 30. So this is 30. Okay. And this value is 90. Because this complete is 120, so 120 minus 30 is 90. So you can see that here the plastic hinge will form at this point if you see the bending collapse diagram. Similarly, this total value I have calculated 135. So 135 minus of 90 will be 45. So this value will be 45, right? And again, this value will be 170 minus of 90. 170 minus of 90, which is 80 kilonewton meter. Okay, so you can see that through the bending collapse diagram, the plastic hinge will form. This portion is collapsing because for this portion 2 plastic hinges are forming, one at this point and one at this point. So this will result in partial collapse of the structure. Okay, here there won't be any plastic collapse. Here in this pan also there won't be any plastic collapse. Okay, and how do we get this bending moment diagram? This thing we have discussed. Okay, so if you have any doubt regarding this, you can write in the comment section. Okay guys, so thank you very much. We'll meet in the next lecture.